This is lecture 4 in week 11. Okay. So, recall that in the previous lecture we were discussing in detail about the Karmaker's algorithm, right. If you recall the structure, we first convert the given problem into canonical form, take an initial value and use a projective transformation to convert it into 1 by n dot dot 1 by n. Okay. So, the transform problem actually becomes a nonlinear program, but I mean since the solution is 0, we can put it as a linear program, and then we choose the direction and the step size, right, by so the direction is chosen by projecting the steepest descent direction to the feasible polytope, and alpha the step size I did not discuss how, but yeah, it has come somehow by Karmaker's grace. Okay. And we then convert it back to we use the reverse projective transformation to convert it back to the x domain. Okay. We repeat this until the objective value function is close enough to 0. So, all of this works very well if we know that the optimal value of the objective function of the canonical form is 0. Even if we know the optimal value of the standard form, we can use minus v star and get away with it. Okay. But what if we do not? Okay. So, in that case, I mean we started with this problem, right. So, we have two issues. The first issue is regarding the transformation, right. So, but I discussed that when you choose little a vector as all zeros and 1, okay. So, we are somehow getting rid of this issue, okay. But such an issue we cannot get around this issue, because now this will actually become mod C transpose x k minus V star is greater than tolerance, and V star is not something that we know, okay. So, no problem, we will just use the technique that we used in the previous affine scaling method, okay, the duality technique, right. So, if you recall, so the problem that we have at hand, the canonical form of this form means C transpose x subject to so Ax equal to 0, A transpose x equal to 1 and x greater than or equal to 0, right. So, this is the problem that we have, right. So, let us write down the Lagrangian. So, we will have C transpose x plus mu transpose Ax, okay. Would like to write it as B minus Ax. So, here I will write it as minus mu transpose Ax, okay, minus mu transpose Ax. So, if this is an m cross n matrix, so this will have another mu. So, I will write that as mu m plus 1, okay. So, that is plus mu m plus 1 into 1 minus A transpose x or minus lambda transpose x, if that works better, okay. So, now if you in case I mean if we had written these two together, okay, maybe we would have been better off, right. So, I will possibly do that. So, since we have here we have m equality constraints, right, m equality constraints and 1 equality constraint. So, in total we have m plus 1 equality constraints, right. So, we will write down a matrix A tilde, which is A and A transpose, little a transpose, okay. And so, the B here, okay, turns out to be B tilde, which is m zeros and a 1, okay. So, A tilde is now an m plus 1 cross n matrix, and this is m plus 1 cross 1 matrix, okay. Now, I can write this as min C transpose x subject to A tilde x equal to B tilde and x greater than or equal to 0. Okay. Note that there is no change in x, I have just changed the representation of these m plus 1 constraints in this form, okay. And now, if you actually write down the Lagrangian, right. So, L of x lambda mu is C transpose x minus plus mu transpose into B tilde minus A tilde x minus lambda transpose x. Okay. So, when you differentiate this with respect to x, you have A transpose or A tilde transpose mu plus lambda is equal to C. Okay. So, you will get the transpose of all this, you will get C transpose minus mu transpose A minus lambda transpose equal to 0. Okay. So, del L with respect to x equal to 0 implies this. Okay. I am going a little fast because I mean this is something that we have derived earlier in the affine scaling method. Okay. So, yeah, you have A tilde transpose mu plus lambda is equal to C. Okay. That is fine, not a problem. And yeah, the complementary slackness condition is that lambda I x I equal to 0 for all I equal to 1 to n. Okay. So, what this tells us is that yeah, so you have A tilde. So, if x I is equal to 0, if x I is greater than 0, then lambda I equal to 0 and thus A tilde transpose mu of I equal to C of I. Okay. And yeah, so if x I is equal to x I is equal to 0 is one other possibility. So, what you know is that so this tells us that x I into A tilde transpose mu of I minus C of I equal to 0. Okay, because if x I is greater than 0, this is 0. If x I is 0, yeah, anyway the product is 0. So, this is true for all I equal to 1 to n. So, if you want to write this in the form of a matrix, it is capital X into A transpose mu minus C equal to 0. Okay. So, sorry, A tilde transpose mu minus C is equal to 0. Okay. So, yeah, this is exactly the condition that we are actually going to use. Okay. So, in fact, we will actually use this. Okay. So, we will, so when you have the optimal value of x and optimal value of mu, you know that this condition is satisfied where x I into A tilde transpose mu minus C is equal to 0. Okay. So, if this is true, the summation is also true, right. So, that is summation C I as I have written C of I, yeah, both are fine, or you can write x I into C of I equal to 1 to n is equal to yeah A tilde transpose. Okay, I will write it this way. Yeah, again it is summation x I A tilde transpose mu of I equal to 1 to n, right. So, yeah, if this is true, of course, the sums are equal. Okay. And what this means is that C transpose x minus, yeah, this is C transpose x, not a problem, and this is actually, so here I mean to write it as a matrix I have to have, yeah, so I can actually write this as x transpose into A tilde transpose mu, right, because A tilde transpose mu is n cross 1 and yeah, so this is fine. Okay. So, or I will write this as x transpose C better equal to 0. Okay. So, that is exactly what I am going to check. Okay. So, the stopping criterion will actually be okay. So, it is going to be x transpose into yeah, either C minus A transpose mu or A tilde transpose mu minus C equal to 0. Okay. Or yeah, it is less than the modulus of this is less than or equal to some tolerance. Okay. So, yeah, if I modify constraint here as what I just mentioned now. Okay. So, in that case we will actually have the algorithm ready for Karmaker's method. Okay. So, going through it once more. So, you are first converting the given problem to canonical form, then so this step is mathematical. I need not have written this, right. So, I mean here I will actually replace this with initializations. Okay. So, so you first initialize x0, okay, of course k equal to 0. So, and converting into canonical form actually means you are given a, little a and c. Okay. So, if you recall what the canonical form is, you have c, capital A and little a, you do not need anything else. Okay. And this is x of 0, k equal to 0, and I can write it here, capital X k is diag of, or capital X 0 is diag of x 0. Okay. Since I am not using bracket here, I will just write it this way. Okay. And yes, so this gets repeated. Okay. But the condition is slightly different. Okay. So, you are going to do while mod of x into a tilde transpose mu minus c is greater than tolerance. Okay. So, that is changing. Okay. So, this is no more the condition is this. Okay. And you need to do an indent. Okay. But I think you can understand all of that from whatever I have written. Okay. So, fine, let us actually work out one example, okay, and we will start with our favorite example, okay, which is maximize x2 subject to x1 greater than or equal to x2, x1 plus x2 less than or equal to 1 and x2 greater than or equal to 0. Okay. So, if you recall, the standard form of this is just to note what is going on, you are actually maximizing x2 when the feasible polytope is a triangle with vertices 0 0 1 0 and half half, right. So, the standard form is min minus x2, right, subject to the condition that A is the following, it is minus 1 1 1 1 0 1 minus 1 1 0 1, and this was x1 plus x1 minus x2 x3 and x4, okay, and this was 0 1, okay, and of course all of this has to be greater than or equal to 0, okay, all 5 components has to be greater than or equal to 0. Okay. So, this is the standard form. Okay. Now, in canonical form, what we have to do is first introduce one more variable x5, which is equal to 1 always, right, and so this has to be brought in here, right. So, that is I mean so this equation becomes minus x1 plus x1 minus plus x2 plus x3, and this is 0. So, that is equal to 0, and the second equation becomes x1 plus minus x1 minus plus x2 plus x4 minus x5, okay, and you add another constraint where x5 is equal to 1. Okay. So, the canonical form turns out to be, so you will have 3 rows, right. So, one is minus 1 1 1 1 0, next is 1 minus 1 1 0 1, this is 0 and minus 1, right. So, x5 needs to be added. So, this is 0 and this becomes minus 1, and here you just have all zeros and a 1, okay, and this anyway is x1 plus x1 minus x2 x3 x4 and x5, okay, and so here it is actually 0 0 and 1, okay, and this is x greater than or equal to 0, nothing to change here, and since we are looking for c as well, I will change that as well. So, this is 0 x1 plus 0 x1 minus plus minus 1 into x2 plus 0 x3 plus 0 x4 plus 0 x5. I mean I will so assume that we do not know V star, right. So, I will just put it as 0, anyway it does not matter, I mean we are convinced that the answer will arrive, right. So, fine, let us write down the code for this particular example. Okay. Yeah, so this is affine scaling method. So, let us start with Karmaker's method. Okay. Fine, we start by importing numpy, and yeah, A is the 3 cross 6 matrix which I just wrote down, minus 1 1 1 1 0 0 and 1 minus 1 1 0 1 0, and the last is 5 zeros and a 1. Okay. So, this is A, and A is just little a is just the last row, right. So, I will just write it as A of minus 1, the last row, right, and C is, yeah. So, you had 2 zeros, minus 1 and 3 zeros. Okay. Fine. Now, we need to choose a starting point. We will choose 0.1, 0.05 which we chose last time, right. So, yeah, so you have to fill the other ones as well, and this we will write it as 1. Okay. So, because x n plus 1 is always 1. So, keep that in mind. So, x 5 is 1. Okay. But these, so when I write x 1 minus x 2 greater than or equal to 0, right. So, the remaining is 0.05. So, that is the reason you need basically you need Ax equal to 0, right, for the first two rows. So, you can see that it is minus 0.1 plus 0.05 plus 0.05, that is 0. Now, here you have 0.1 plus 0.5 is 0.15. Oh, I am sorry, this should be minus 1. Yeah. So, yeah, now it is 0.1, 0.05, 0.85 and minus 1. So, that is 0 as well. Okay. All right. So, now capital X is the diagonal of x. Okay. Can we write k equal to 0 and mu equals the inverse of A x squared A transpose, and you multiply that with A x squared C. Okay. So, all of them are defined before. Okay. So, I will print the required values k, x, and yeah. So, the stopping criterion if you recall is np dot abs of x dot A transpose mu, right. So, that is A transpose mu minus C. Okay. So, again that is going to be our constraint. Your absolute value of x dot A transpose mu minus C should be, I mean when it is greater than the tolerance you continue. Okay. Yeah. So, the first step is choosing D, right. D, if you recall, is I minus 1 1 transpose by n, right. So, yeah, I will show that to you. Yes, I minus 1 by n 1 1 transpose into x minus x into a mu minus c, right. So, this is np dot I of, okay, n I have not defined, I will just define that as the shape of x, right. So, yeah, that is I, and here I have to write np dot ones of n comma n by n. So, 1 into 1 transpose is 1 is a column vector of 1s, 1 is a row vector of 1. So, when you do a matrix multiplication you have a matrix of all 1s, right. So, 1 1 transpose is 1s of n comma n, right. So, I have to use another bracket. and I divide it by n. Okay. So, that is I minus 1 1 transpose by n. You multiply that with x and you multiply that with A transpose mu minus c. Okay. So, that is D. Now, y is NP dot 1s of n by n plus okay. So, the denominator now is 1 by 3 into square root of n into n minus 1, okay, into d by np dot lin alg of dot norm of d. Okay. So, I have just writing step number 5, yk plus 1 equal to the 1 vector by n plus 1 by 3 root n into n minus 1 into dk by norm dk. So, that is exactly what I have written here. Okay. So, we have written down the expression for y. Now, we will now you have to do the reverse projective transformation, which is xk into y by A dot xk into y. Okay. So, again it is just x dot y x at y by A dot x at y, nothing else. Okay. Now, you have to write k equal to k plus 1 and of course, the mu I mean okay, capital X has to be the new diagonal matrix and mu needs to be replicated. Okay. And again we will print the usual values k, x and the absolute value of x dot A transpose mu minus c. Okay. So, fine, we have replicated all the steps. Let us see if it works. Okay. Okay. So, you can see the answer here, it is half, 0, half, 0, 0 and 1. Okay. So, the last one is supposed to be 1 anyway. So, we just have half and half as the right answer, right. So, we got the answer in 47 steps. Okay. And so, we have you can see that the algorithm is very similar to what you had for the affine scaling method, right. So, it is just that instead of using a linear transformation, you are using a projective transformation, and instead of the canonical form, the standard form, we are using the canonical form. And because of this, you also have a change in the stopping criterion, right. The stopping criterion turns out to be the absolute value of x dot A transpose mu minus c should be less than or equal to the tolerance. And one of the key things that works here is the value of alpha. Okay. So, the value of alpha is key in having the polynomial algorithm, right. So, that is I mean the number of steps should not go to 2 power n, right, like what we had for simplex method, right. So, here I mean we have a guarantee that such things will not happen. Okay. So, in the next lecture we will work out a few more examples, and I will then let you know about the I mean a little bit about the polynomial order that the Karmaker's algorithm is boasting of. Okay. With that we will end our discussion on Karmaker's algorithm. Thank you.